All right, welcome back to Easy Math with Nick. Back-to-back videos, um, consecutive days with video number 9 right after video number 8 yesterday. Today's topic is not the statistics, however. We're going back to calculus to talk about the derivatives of inverse functions today. So I don't know why my writing is sort of angled. Let me make my computer straight so I don't write at an angle. So before we begin talking about how to find the derivatives of inverse functions or how to do questions involving that, let's do a brief review of how to find an inverse function. So the example I enumerated here, if f of x equals radical square root of x minus 1, find f inverse, the inverse of f. So the first step we do here was we set f of x equal to y. So we say y equals x minus. This is to make things easier and more mentally palpable when we go to step 2, which is we swap the y's and the x's. We swap the x and the y. So we're going to have x equals y minus 1. And this is a very important step. Two sort of qualities of inverse functions arise from this step here. One being if we have f of x equals y, or just f of x equals some value. I'm not going to use y because we already use y. F of x equals omega. Don't ask why I'm using Greek letters. F inverse of omega equals x. So that's to like sort of show here that we're flipping the x and the y's when we at the step 2 here, which seems obvious, but it's really a nice trick that we can use to help solving some questions that would be very confusing otherwise. So, for example, you might be given f of 1 equals 2, but you're not given an f inverse of 2. And what would f inverse of 2 be? 1. You would know that because they're inverse functions, but that's just a little trick that you would typically see on, I think, the calculus AB exam. That's something that showed up, at least on maybe a practice exam. Oops. So that's relevant for our discussion today. And also, swapping the x and the y's results in a symmetry on the xy axis about the line y equals x. So we're going to see a symmetry about this line. That'll become more apparent when I finish this example and graph both the inverse and original functions. So that'll become more apparent as we continue. So our third step here is now to solve for y. So step number 3, so we're going to have x squared equals y minus 1. Y equals x squared plus 1. So now we solve for y. But notice here that let me think. Our domain here only accounts for x's greater than or equal to 1, because that was what was in our starting example here. We had x could only be greater than or equal to 1 because of the radical. We can't have a negative under the radical. So that still carries down here, if just to be technical here. But for illustration's sake and for what we're covering today, I'm not going to be concerned about domains, because that just makes our conversation more complicated than it needs to be. But just for so I don't get corrected in the comments, we do in a more formal setting than this simple video I'm making. You want to keep that in mind as we take the inverse. That's why, for example, even though the functions x squared and square root of x are inverses, when you graph both of those, x squared looks like this, and the square root of x, it only has something in the first quadrant, not the second quadrant. That's why you don't. It's I'm getting too technical here, but you can kind of see where I'm getting at, hopefully. Spent too much time talking about that. So now that we solved for y, our fourth step is to write y as f inverse of x. Because now we solve for that y, which is different than the y we had up here, because we're swapping the x and the y's. Which is why maybe you don't like that notation. And so if you want to just keep it as f of x the whole time and then switch it to f inverse of x to make it more clear, so you do it in less steps. For example, instead of having y here, we would have f of x. And instead of having y here, we would have f inverse of x. Not f prime of x, f inverse of x. If that's more clear to you, you can do it that way, and that also eliminates a step. But I feel like this way is more intuitive for me, at least. So there's that. All right, so now we have our inverse function. If we graph both of these functions, taking into account that the domain here is going to be 1 to infinity, where 1's inclusive, as I stated before, we can graph both of these functions. This being x equals 1. So our original function was, I'll do the original function in black and this in red. So I'll just circle this in red. And I'll circle the original function in green. So our original function is going to be square root function shifted 1 to the right. So it's going to look like near, like that. And the and our other function, our inverse function, is going to be x squared shifted up 1 vertically. So, but we're starting at 1 here, so we're going to have 1 comma 2. So it's going to be something like this. Something like that. And I know I drew this very crudely here, but if I drew it a little more better, you can see that these two functions are symmetrical along the line y equals x, so they are inverses. So if you have the time to take out and graph, that's one way to test that they're inverses. But there's another test, and this is very important for our discussion today, to test if two functions are inverses. There's I won't go into technically why this the technicalities behind why this works, but if f I'm going to write the word if first. If f and g, two functions, are inverses of one another, then f of g of x equals g of f of x, equals x. So for our, this is very important for today, so I'm going to box this in green. So for our example that we had up here, our inverse function was x squared plus 1. So if we did f inverse of f of x, for our example up there, I'm not going to draw an arrow, but you get the point. We're going to have in parentheses, within that nested inverse function, we're going to have x minus 1, radical x minus 1 squared plus 1. So this is going to yield us x minus 1 plus 1 equals x. So we could check that off, and that passes the test for that this is indeed, we indeed have two inverse functions here. The functions are inverses, I meant to say. This also conversely works if we do f of f inverse of x. So this is going to get us, what was our inverse function? I'm sorry, what was our original function? So it's going to be radical x squared plus 1 minus 1. So radical x squared equals x. So it passes the test with that too. Because it passes both tests, we know that these functions are inverses of one another. And so this fact here is really important for how we're going to very simply derive an expression to solve for derivatives when we know that two functions are inverses of one another. So with this rule that we have here, without even giving an example, I'll jump right into it. If f and g are inverses, this is still true for down here. F of g of x equals x. If we are so inclined to take the derivative of both sides, we will have a chain rule scenario where we'll have f prime of g of x times g prime of x equals 1. ddx of x is just 1. And so if we want to solve for g prime of x, we would have g prime of x equals 1 over f prime of g of x. If you wanted to, as above, if you're not comfortable with having g, you could also say f inverse, but I feel like that's a little pedantic. So there you go. We have an expression to find g prime of x without even knowing what that function is. If we what the g function is, as long as we know enough information to find f prime of g of x, whatever that is. Usually questions like this will give you a table of values, so you'll have to solve it using like the tabular method, so to speak, which is a common question type on many calculus exams, including, as I stated before, I think I mentioned the calculus AB exam, AP calculus AB exam. So that is pretty cool. So that's the relation here between relation that we just found. So don't know where I was going with that sentence. So let's get into an example. If you can see at the top left, it's sort of getting late where I am. So apologies if I'm a little bit incoherent, but I think I'm doing a good job so far. Let's make a table. So x equals 1. I'm filling in some values here, just some arbitrary values. Oh, for illustration's sake, I think I'll leave this blank. I'll put a question mark here, and we want to solve for this, I think. So, and we'll have 14 here. Let me make sure that lines up. Okay, I think we're good. So first, let's find g of x. We'll need that to find f prime of x. I'm sorry, g prime of x anyway. So once again, f and g are inverses. Not gonna write that out. Okay, so how do we find g of x? Well, I was pretty keen in the number choices I made here. We know that according to the table here that f of 1, functional value for f at x equals 1 equals 5. So because f and g are inverses, this property that I stated up here applies. So g of 5 is equal to 1. So we can get rid of this question mark that I put here and put a 1. Now, what about g prime of x? I'm sorry, g prime of 5, which is what we're solving for here. Well, let's use the equation that we found up here now. So g prime of x is going to be 1 over f prime of g of x. So what is our, we're trying to find g prime of 5, equals 1 over f prime of g of 5. What is g of 5? We found that's 1, so we're going to bring that. Let me make that arrow a little better. Oopsie. Oopsie daisy. We're going to bring that there. So we're going to have g prime of 5. 1 over f prime of 1. What's f prime of 1? That's something we can see in the table here. That's 7. So g prime of 5 equals 1/7. There you go. Look at that. So we have our answer here. Whoops. So this is a very common question format that I know for the AP Calculus curriculum, which is why I use this as an example here, because they give you a table with some incomplete values and also extraneous values that, well, not extraneous, that's not the right word, but extra values that you don't necessarily need to solve the question. Do we need to know what f of 5 is to solve the question? Not necessarily. Well, unless we wanted to do this an alternative way. I just chose these numbers arbitrarily, but say we started off by saying, let's see here, f prime of x. Instead of having f of g of x, let me just take a moment to pause here so I don't go on a tangent. I'll be right back. I'll have some things drawn on the screen to show another way to solve this question using what's given and see if we get the same answer. I'll be right back. Okay, so there is an alternate way to solve this. If we instead of having f of g of x up here, and we had g of f of x for whatever reason, because we know that f of g of x equals g of f of x from up here, what I had with the asterisk, to have the arrow be there, we know that f of g of x equals g of f of x equals x. So we can start with this instead and get a very similar looking equation here that, for our derivation up at top. So if we wanted to find g prime of 5, when is f of x equal to 5? At x equals 1. So we would have f prime of 1 equals 1 over g prime of 5, because f of 1 equals 5. If we want to then solve for g prime of 5, we would have g prime of 5 equals 1 over f prime of 1. And this is essentially the same as what we had up top in the other example, so it would be 1/7 either way. So no matter what way you solve this question, you will get the same answer as 1/7. So there you go. I think that's all I wanted to cover today. I think we hit the ground running. I think we did a good job. So thank you. Thank you for sticking by. This was surprisingly on the shorter side, even though it's nearing 20 minutes, I think. So regardless, thank you. This one was a fun one.